What's the acceleration? 30. To 1,000. What's the acceleration here? 30. 3 1,000. Whoop. What's the acceleration here? 30. And so the acceleration is always 30. And so this is a problem that we would call a constant acceleration problem. It always has an acceleration of 30. All right, so maybe that's the easiest of the three columns. Although this one's not too hard. And this one is pretty hard. Okay, so let's do the velocity. What would the velocity be after 1 second? And I should emphasize, this is instantaneous velocity. Well, hopefully that's pretty straightforward because, again, what does this mean? Acceleration means change by 30 centimeters a second each second. All right, so if I was at 0 and I changed by 30, how much would I have after 1 second? 30. Exactly. So how much would I have after 2 seconds? I hope you're seeing it. 60, right? It says go up by 30. That's what this whole thing means. Change your speed by 30 centimeters a second each second. All right, so if I'm going 60 after 2 seconds, how fast would I be going after 3 seconds? Yeah, 90. Go up by 30. And then how fast would I be going after 4 seconds? Yep, 120. Because you are increasing by 30 centimeters a second each second. Now, I would say I did this column a little bit more conceptually than mathematically. Let me not take the time to do every step. Maybe I'll do this one right here. Maybe a good question to ask would be, what is the speed after 3 seconds using these formulas? Okay, well, this then would be a very useful formula. Because we just said the acceleration is 30, and that is equal to the change in speed over the time taken. And so just like I was showing you earlier in the lecture, if I give you any 2 of these, you can find the third. And so here's the third, the change in velocity, because I'm saying after 3 seconds. So if I put in a 30 centimeters per second squared for the acceleration, and down here, I put in 3 seconds. And then I move this to the other side, so this becomes 3 seconds multiplied by 30 centimeters per second squared. I would get the change in velocity. And let's do our unit analysis again. The 3 times the 30 is the 90. A second is in the numerator, and then there's a square of them, or 2 of them in the denominator. So I will cancel 1 each, and I will be left with centimeters per second, which, by the way, is good, because I'm asking for the change in speed, and the change in speed should be measured in centimeters per second, and sure enough, it came out to be centimeters per second. So my unit analysis works really well. Now, this, of course, is the change in speed. So maybe I should write that as final speed minus initial. But for this problem, the initial speed was 0. And maybe I should put my unit 0 centimeters per second. So when I bring the 0 over to this side, I end up with a final speed of 90 centimeters per second. And notice this is instantaneous speed. So this is the final instantaneous speed. And sure enough, it matches what we got earlier when we did it conceptually. So whether we do it conceptually or whether we do it mathematically, hopefully you'll do it both. Did you notice on the homework, you have some questions, half of your homework is conceptual questions, and half of them are under that category of exercises. And so those are your numerical, those are your 2 categories. Now, maybe I'll do another one from this chart before we move to the, or this column before we move to the next column. But if I go ahead and I say, could you tell me the speed after 4 seconds? But let's do it a little different. Let's do it this way. Let's say that I told you your speed is 90 after 3 seconds. Your acceleration is 30. What is your speed after 4 seconds? Now, obviously, conceptually, that's going to be easy because, hey, well, you already go 90, and you're just asking about a second later, and you change by 30, so 90 and 30 make 120. So we've already done that conceptually. But if we do that mathematically, it would look like this. We would say A equals change in velocity over time, and the acceleration is the 30 centimeters per second squared. The change in velocity, then, let me just leave for a moment as change in velocity. But in this case, the time difference would be 1 second. So notice this is a delta t. This is saying, what is my change in speed from this moment, 3 seconds, to this moment, which is 4 seconds. And so that's one of a couple things I wanted you to see, that there's a little subtlety there. This is 1 second. It's not 3 seconds. It's not 4 seconds. It is the change in time between those two. So 1 second. Now if I bring this to the other side, nothing real complicated other than watch your units again. Because 1 times 30 is just 30. But the big thing here is seconds would cancel off and you would get centimeters per second would be your change in velocity. Okay, so you change by 30. But then if you take this and say, well, a change in velocity is its final speed minus its initial. And I'm asking you for what is its final speed? What is its speed after 4 seconds? Because its initial speed was the 90. That is the speed after the 3 seconds. I can then take this and bring it over to here. And so it becomes a plus sign. So 90 plus 30 is now 120 centimeters per second. And so, bring this over to here. And so I should write it as final speed is now 120 centimeters per second. And sure enough, that agrees with what we got conceptually. So again, I hope you're seeing here what the difference is between speed, velocity, acceleration, and of course, more importantly, is you could do it both ways, right? You could do it kind of conceptually understanding what is meant by acceleration and by what is meant by speed. We'll do it again with the harder one. And then you could also do it with a calculation. And so you're going to be asked to do both. Sometimes a chart to make it conceptual, and sometimes an equation. Okay, well, let's do the harder one. Let's fill in this column. And so let me ask you this. How far is it after 1 second? Now, if you want to watch it again, I'll roll it in here, but here it is. So I'll start with it here, and I let it go. 1/1000, so right here, right there. How far is that? Well, I set this up a long time ago, so I'll probably have to go back. But that other equation that said this, velocity is equal to the change in the distance divided by time taken. And so if I wanted to know how far this is, I guess on this side of the equation, I would put 1 second. Here I would go the change in distance. Here's the important part I want you to see. What do I put here for velocity? Do I put 30? No, that was that subtlety between average speed and instantaneous speed. Do you remember that subtlety? See, let me come back over here. This would be a real easy problem if it had been going 30 centimeters per second for the whole 1 second, right? I mean, 30 centimeters per second means go 30 centimeters in 1 second. But if you look carefully at this problem, it starts at 0 speed and goes faster, 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 faster. And when it gets here, we're saying it's going 30. We're not saying it went 30 for the whole second. If it was, it would be very easy to do this conceptually. We would just say, well, 30 centimeters per second means go 30 centimeters in 1 second. I think that's why when I do this class face to face and I point to this box and I say, what number goes here? 5 or 6 people in the audience go, oh, that's a 30. No, it would only be a 30 if it was going 30 centimeters a second for that whole 1 second. And so I want to emphasize, if you're going to use the whole distance from here to here, I didn't give myself enough room here, average velocity, I think I can squeeze it in there. But if you're going to do this whole calculation, you can't put the instantaneous. It's the average. And then sadly, that makes this stuff a little bit harder because, wait a minute, I don't have average. I have instantaneous. Well, I can get average real easy. Because think about this. I've got 2 numbers here. It starts at 0 and it goes up to 30. So if I gave you those 2 numbers and I asked you to average it, could you? Yeah, I guess you would do this, right? You would say, okay, well, to get average, and I'm going to use the bar. I don't know if you're familiar with that mathematical symbol, but that's kind of the traditional mathematical symbol of how we indicate an average. So we like to use it. So this is average. And so I would take my 2 numbers, 0 and 30, and add them together, and then divide by how many numbers do I have? I have 2. And so my average speed is going to be 15. Now I suppose I should watch my units here. This is centimeters per second, and so this is an average of centimeters per second. The 2 doesn't have any units. So what I can do here is put 15 centimeters per second for my average. And then my change in distance with 1 second. I can then bring this to the other side and I get 1 second times 15 centimeters per second. And mathematically, 1 times 15 is pretty easy. That's just 15. And then seconds would cancel with seconds, and I would get 15 centimeters. And so this is saying that the distance between here and here should be 15 centimeters. Another way of saying the same thing is my average speed is 15. And if I was going 15 for the whole 1 second, I would have gone 15. And so I'll say it again. Notice a very common mistake is to put a 30 here. Because people put a 30 here. They put a 30 here, they put a 1 second there, they get a change of distance of 30, and that's not correct. Okay? Well, let's try this again so that you can maybe see another one here. How about I do this? How about I do the very end of it? Okay? After 4 seconds. And I'll do it twice. I'll do it conceptually, and I'll do it mathematically. Let's just look at the whole 4 seconds, right? If we started way at 0, and we went faster, 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 and we went 120, what's our average? It's right in the middle, 60. So if I was going 60, that means I go 60 every second. So there's 4 seconds here. So it'd be 60 and 60 and 60 and 60. So 60 and 60 is 120. Another 60 is 180. Another 60 is 240. All right, there it is, 240. And that's what I would mean conceptually by this. But let's try it mathematically. Let's do exactly the same that we did here. I'll start with that formula. I'll erase this one. I'll even erase this one. And I'll put in my first line right here and go 4 seconds down below. So there's 4 seconds. Okay. This, remember, is average, not instantaneous. So, like we did a moment ago, let me put average. And for the whole 4 seconds, we would have started at 0. And 4 seconds later, we would be going 120. So if I take those two numbers, add them together and divide by 2, right? Divide by 2 because it's an average. Add them together because, again, we're trying to get an average. By the way, don't confuse the calculation for the average speed versus the calculation for the change in speed. Because the change in speed, you subtract the 2. And we did that earlier. But that's not what I'm asking here for the subtraction of the 2. I'm asking for the average, so be careful on your mathematics. Sometimes you'll be asked to subtract the 2, which is the change in speed, as we did earlier, but other times you'll be asked for the average, which I'm doing now, and so you add them together. Anyways, this gives me a 60. And 60 centimeters per second is the average, and of course I did that a moment ago conceptually. So if I put that into here, this is then 60 centimeters per second, and I can get the change in my distance. And so if I bring this 4 over to here, I would have 4 seconds, then multiplied by 60 centimeters per second. And then I would get my change in my distance. And then, of course, the seconds would cancel off. The 4 times the 60 is the 240 centimeters, and that's that change in distance. So there it is, 240. And maybe just to complete this chart, I'll do this kind of quickly here. But maybe you could see, and there's a lot of ways we could do it. We could go from 0 to 2 seconds. But we could also look at the average from 1 to 2. See, the average from 1 to 2 is 45. Which means I would go 45 centimeters during this second. And I've already gone 15. So that must be a 60. 45 added on to the 15. Or I could have done the whole thing. I could have looked here and said, well, from 0 to 60 is an average of 30. And 30 for 2 seconds would give me 60. So either way you want to do it, you're going to get there with 60, whether you do it conceptually or write out the numbers. And maybe right here's a good one. A little bit harder. But if I take a 60 and a 90, that's 150. Cut that in half is 75. And so that makes 135 right there. Because the average speed is 75. And so I should go 75 during that 1 second. And you can run the numbers there and get the same thing. So that's really a good exercise of hopefully you've seen the difference between these two. But let me show you a couple other ones. Here's a fun one to see. Maybe I should look at our time-wise.
Hour and a half.
And so we're way over our hour and 15, which is way past our break time. Sorry, I just got so excited about this. And I'm trying to get the whole chapter in one lecture. But why don't we take our break? I know that we're remotely, so you guys actually could have taken a break anytime you want. Just hit the space bar and pause. But I'll just try to stick like in a normal class. And so let's take a break, and when we come back, let's do a few more of these before we move on into the next chapter. And if you're looking at the syllabus, you'll see that the syllabus has us, just starting the next chapter anyways, not finishing it. So that's what will end up happening is we'll finish this chapter, we'll start the next one, but we won't finish it. All right, so we'll cut it there.